Hello all, welcome to this course on Elements of Mechanical Engineering. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. We are in the first module where we are studying energy sources and basics of thermodynamics. In the previous lectures, we have seen different laws that will guide the work of thermodynamics, and we have seen many numerical examples on thermodynamics. In today's lecture, we are going to see some problem solving on the concepts of work, internal energy, and enthalpy. So let us see the first example for this lecture, and the question goes like this. For a particular reaction, the system absorbs 6 kilojoules of heat and does 1.5 kilojoules of work on its surroundings. So there is a system here. The system is given here where it will do 6 kilojoules of work and 1.5 kilojoules of work is done on its surroundings. So the work is taken out of the system and heat is added to the system, that is 6 kilojoules. Now what are the change in the internal energy and enthalpy change of the system? Now so we have to calculate the internal energy and enthalpy. Now let us see what is the given data. So first of all, the given data in this question is 6 kilojoules of heat which is added to the system. So it is taken as positive sign. See here, it is taken as positive. If the heat is taken out of the system, then it is taken as negative. And work done. Work done is done by the system on the surroundings. So the system has absorbed 6 kilojoules of energy or heat and it has done some work on the surroundings. So because the work is taken out of the system, so we have to use negative sign here in order to indicate the work is done by the system. Next, what are the things we have to find in this question? So we have to find the internal energy. We have to calculate the internal energy, that is delta U, and also enthalpy. We have to calculate the enthalpy change. How much enthalpy has been changed during this entire process. Now, let us solve this. So, by using the first law of thermodynamics, we have this equation, that is delta U is equal to Q plus W, whereas delta U stands for the change in internal energy. Delta U is nothing but the internal energy change, where Q is the heat added or removed to the system, and W is the work done by the system or work done on the system. Now from the given question or the given data, we can simply write Q is equal to 6 kilojoules. So this is the heat added to the system. So we are taking it as positive. If the heat is removed from the system, we will take a negative sign, and the work done by the system. So work is taken as negative, which is 1.5 kilojoules. Now the total value is 4.5 kilojoules of energy. So this is the change in enthalpy or internal energy of the system. Okay, when I take a system, the heat supplied or heat removed, the overall net heat is 4.5 kilojoules. So this is delta U. And then delta H is equal to, so what we are doing here, we have to calculate another thing. So let us go back to the question. Here we have to calculate two things, change in internal energy, that is delta U, and enthalpy, delta H also we have to calculate. So far we have calculated delta U, we have to calculate delta H. So delta H is nothing but, so this is a normal process. There is no complications given in the question, like there is no isothermal adiabatic process or isobaric process or isochoric process. This is a very normal process where the heat is supplied to the system and it has done some work. Okay, so the heat supplied is directly equal to the change in enthalpy. So change in enthalpy delta H is directly equal to the heat added to the system, that is represented with QP. So this is equal to 6 kilojoules. Simple. So delta H is equal to 6 kilojoules. So from this, we have completed the solution for this question. So the change in internal energy is 4.5 kilojoules and change in enthalpy is 6 kilojoules. So that is all for this problem. Now we'll go to next example. So this is second example for this lecture. And the question goes like this. An ideal gas expands from a volume of 6 dm cube. So this stands for the decimeter cube, and it has risen up to 16 decimeter cube against a constant external pressure of value that is given here 2.026 into 105 Newton per meter square. Now what we have to do is we have to calculate the enthalpy if change in internal energy is 418 joules. So the question is very confusing. We have to calculate enthalpy. We'll see first what is the given data. Initial volume V1. Initially the volume V1 is nothing but V1 is equal to 6 decimeter cube. 6 decimeter cube dm cube. This can be rewritten as 6 into, so I'm converting this into meters, 6 into 10 power minus 3 meter cube. So this is the initial volume. So this is one thing. And then the final volume V2. V2 is equal to 16 decimeter cube, which is equal to 16 into 10 power minus 3 meter cube. So this is V2, the final volume. And also there is an external pressure which is represented with P suffix EXT. External pressure is 2.026 into 105 Newton per meter square. So this is the pressure that is being applied on the system. And then the change in internal energy, delta U. Delta U is also given in the question, which is 418 joules. So this is the given data. We have written very clearly. There is V1 initial volume, V2 final volume, external pressure applied on the system PEXT, and change in the internal energy delta U. So these four things are given in the question. We have to calculate the enthalpy change. We have to calculate delta H. Okay. Now we'll see. So first of all, for calculating the change in enthalpy, we have to calculate the work done by the system. So that is why we have taken this formula, that is W is equal to P into delta V. This is the normal formula. Like we have seen in the definition, the work done by any thermodynamic system can be calculated with the help of an equation, that is pressure multiplied by change in volume. And here the pressure is external. A pressure is applied externally. That is why we have to take a negative sign here. So minus P external into delta V. Okay. Now using this equation, we can simply calculate P external is nothing but minus 2.026 into 105. So this is given in the question itself. And delta V, that is V2 minus V1. So it is already there. V2 minus V1 is nothing but, we can simply write 16 minus 6 into, so the 10 power minus 3 I am writing separately. Okay. So after calculating this whole value, we will get minus of 2026 joules. So this is the work done by the system on the surroundings. Okay. So work done by the system. Now using first law of thermodynamics, why we have calculated the work done? Because we have to calculate the change in enthalpy. So in order to calculate the enthalpy value, that is nothing but the Q value, we have to use first law of thermodynamics. Like from first law of thermodynamics, we have delta U is equal to Q plus W. So out of this equation, we already know delta U, which is given in the question. And Q value we have to calculate ultimately, and W value has been calculated just now. This is W minus 2026 joules. Now we will substitute these values in the formula, and delta U is given in the question, that is delta U is 418 joules. So delta U is nothing but 418 joules, which is equal to Q we have to calculate plus this is minus 2026 joules. So from this equation we can simply calculate the Q value, which is comes to be 2444 kilojoules of heat. Now in the question we have been asked to calculate the change in enthalpy, that is delta H. Here there is only one reaction taking place, that is an amount of Q is being added to the system, because we got the Q value as positive. This is the energy that is added to the system. So the change in enthalpy is directly equal to the Q value. So delta H is equal to Q, which is equal to 2444 kilojoules. So this is delta H value. Okay. So in this question we have calculated the delta H, before which we have calculated work for substituting this in the equation. So in this question we have to calculate only delta H. We have done that. So delta H value is equal to 2444 joules. So sorry, this is joules. So this is the answer for the second example. Now we will go to the third example. But before going to the third example, we have to understand what kind of formulas we are using in order to solve this question. Once study the question. So this is the second example itself. We have the change in volume and also the pressure. We have to calculate enthalpy if the change in internal energy is given. So for calculating enthalpy, we need to use the first law of thermodynamics formula, that is delta U is equal to Q plus W, this formula. For using this, we have to know what is the value of work done by the system or on the system. So for that we have used a second equation, that is P into V2 minus V1. So this is pressure into volume, which will gives you the work done. Now this work done has been substituted in the first law of thermodynamics equation, where we got the delta U value. After that we already know the delta U, which is given in the question itself. So we have finally calculated the change in enthalpy. Okay, now we'll go to the third example, where the question goes like this. A sample of gas absorbs 4000 kilojoules of heat. 4000 kilojoules of heat. And first question in this is, if the volume remains constant, what is delta U? Here the volume is constant, we have to calculate delta U, change in internal energy. And second question is, suppose that in addition to absorption of heat by the sample, the surroundings does 2000 kilojoules of work on the sample. Then what is the change in internal energy? So second question is another condition where there is an absorption of heat by the sample. The surroundings does a work of 2000 kilojoules on the system. So then we have to calculate delta U again, change in internal energy. And the third question, C point, is, suppose that as the original sample absorbs heat, it expands against the atmospheric pressure and does 600 kilojoules of work on its surroundings. Then what is the internal energy? So in all the three cases, we have to calculate the internal energy itself. But depending on the different conditions, we have to modify the equations and we have to calculate the values of internal energy. Now, let us see. How do we calculate? How do we calculate the internal energy in all the three different cases? Okay. First, we'll write what is the given data here. We have to write the given data. A gas absorbs 4000 kilojoules of heat. Here 4000 kilojoules of heat is absorbed. by the system. And in the first question, if the volume remains constant, volume is constant, what is delta U? We have to calculate delta U when volume is constant. Delta V is constant. And second question is, we have to calculate the value of delta U when a 2000 kilojoules of work is done. 2000 kilojoules of work is done on the sample by the system. Okay. Now this is taken, W is equal to 2000 kilojoules. And third one is when 600 kilojoules of work is done on the surroundings. 600 kilojoules of work is done on the surroundings. Then again we have to calculate change in internal energy. So this is the given data. Now we have to calculate the internal energy in 3 different cases. Now let us see part 1, that is part A. So here 4000 kilojoules of heat is absorbed by the sample. So this amount of energy we have taken it as Q is equal to 4000 kilojoules, and change in volume. This is given in the question. The volume is same because delta V is equal to constant. Okay, delta V is constant. So that is why here delta V is taken as 0. Delta V should be taken as 0. Now we have to calculate delta U. For doing this, we will use the first law of thermodynamics as it is. Before that, we have to calculate the work done also. So, first of all, the work done is equal to W is equal to P external multiplied by delta V. Here, the P external will have a negative sign. Why should it have a negative sign? Okay, because we know from the past experience that a pressure should be applied on the system. Okay, so that is why it is always taken as negative. But in this condition, the change in volume is 0. There is no change of volume. So which indicates that this entire thing will goes to 0. So W is equal to 0. Work done is equal to 0. Now from the first law of thermodynamics, which is delta U is equal to Q plus W. Here W is 0, the work done is 0, whereas Q value is nothing but 4000 kilojoules. Now what happens? The change in internal energy is directly equal to 4000 kilojoules, which is equal to the enthalpy added to the system. Okay. So when some amount of energy is added to the system, it is called enthalpy, and heat is added. Now this enthalpy is directly equal to the change in internal energy because there is no work done. Why? Because there is no work done? Because there is no pressure, there is no change in the volume. Even though there is a pressure exerted on the body or the system, there is no change in the volume. That is why the enthalpy is directly equal to change in internal energy, that is 4000 kilojoules. Now we will calculate the part B. Here the same thing, the energy is same, the heat supplied to the body is 4000 kilojoules, and W is equal to work done. Work done is given in the question, that is 2000 kilojoules work done by the surroundings on the system. Okay. See here, the work is done on the system by the surroundings. So it is taken as positive. If the work is done by the system, then it is taken as negative. Now here, we have taken the 2000 kilojoules value as positive, and we can calculate the change in internal energy by simply using the formula delta U is equal to Q plus W. Q is nothing but 4000 plus W is nothing but 2000. So which will gives you a value of 6000 kilojoules. So this is positive, obviously. So in the second question, that is part B, we have the change in internal energy as 6000 kilojoules. In the first condition, we got it as about 4000 kilojoules. In part B, we got 6000 kilojoules. Now we'll see how much of a change in internal energy in part C. Here, Q is equal to 4000 kilojoules, which is given in the question, and W is equal to minus 600 kilojoules. See here, we have written in the previous slide that work done by the system is taken as negative because we are removing the work from the system. So this is taken as negative. So here 600 kilojoules of work is done by the system on the surroundings. So it is taken as negative value. So negative 600. So the 600 kilojoules of energy is taken out of the system. And we have to calculate the change in internal energy simply by using the first law of thermodynamics. We have to write delta U is equal to Q plus W, where Q is equal to 4000 kilojoules plus minus 600 kilojoules. So this is negative when the work is done by the system. So we will get a 600 kilojoules. So we will get a value of 3400 kilojoules. So this is positive, and it is the change in internal energy in the third case or part C. Okay. Now in this question we have calculated like 3 parts are there. In the first case, where the volume is constant, we have the change of internal energy value is 4000 kilojoules. In second condition, where the work of 2000 kilojoules is done by the system, then we got the value as 6000 kilojoules of change in internal energy. And in the third case, where we have the system has some work is done on the system, that is 600 kilojoules, where we got the value as 3400 kilojoules of change in internal energy. Remember, when we calculate the change in internal energy, we have to calculate the work. If the work is given in the question, then it is no problem that we can simply see that the value can be directly calculated. Okay. So this is example 3. Now we'll go to next example. So this is example 4. And the question goes like this. A person does 30 kilojoules of work on 2 kg of water by stirring using a paddle wheel. So this is a general example where we will apply the laws of thermodynamics. So this is where we will get to know how practically we can apply the laws of thermodynamics which we have studied theoretically. So in this question, a person does 30 kilojoules of work on 2 kgs of water by stirring the paddle wheel. While stirring, around 5 kilocalories of heat is released from water through its container to the surface and surroundings by thermal conduction and radiation. So, what is the change in internal energy of the system? So, first of all, let us try to understand this question has multiple fields of thermodynamics to be taken care. That is, we should know the basics of thermodynamics as well as the basics of heat transfer. Heat transfer is also a branch of thermodynamics where we will study the different conducting methods of heat transfer, in which methods the heat will be transferred from one body to another body. There are like 3 basic methods in heat transfer, that is conduction, convection and radiation. So these 3 are the processes by which a heat can be transferred from one body to another body, whereas radiation does not require any medium, whereas in convection it requires a medium which can be of fluid form, and in conduction we need a medium that is of solid form. Okay, these 3 are the modes of the heat transfer. Now in the question we were asked to calculate the the surface, water through its container to the surface and surroundings by thermal conduction and radiation. There are two conditions given in the question where we have to calculate the change in internal energy. Okay, now I am doing this. So let us see what is the given data in this question. Okay, first of all, work done on the system. Now in the given question, work done on the system is nothing but W is equal to 30 kilojoules of work is done on the system. Because it is done on the system, we will take this as positive. Now the weight of the water is given as 2 kilograms and around 5 kilocalories of heat is released. Q is equal to 5 kilocalories. We have to convert this into joules so that we can use it in our calculations. And then we'll see how to calculate this entire thing. First of all, work done on the system is given here. W is equal to minus 30 kilojoules. Okay, minus 30 kilojoules because work is done on the system. So work is on the system, so it is taken as negative. Sorry, this is not positive, this is negative. So the work is done on the system, so it has to be taken as negative, 30,000 joules. And heat is flowing out of the system. Heat is taken out of the system, so it is also taken as negative. So Q out is equal to minus 5 kilocalories. So here, this is minus 30,000 joules and Q is equal to minus 5 kilocalories. Now we have to convert these kilocalories into the values of joules. So for that we have to calculate with a number 4184. So this will convert the kilocalories into joules. Okay. Now see here. First of all, we have W, that is minus 30,000 joules. And Q is equal to 5 kilocalories. I am converting this into 4184. I will multiply this with 4184 and it will give you the value minus 20920 joules. So I have converted the kilocalories into joules. Now by using the first law of thermodynamics, I have the formula delta U is equal to Q minus W. So this is very regular formula from first law of thermodynamics. At least there is one thing we have changed. That is, we have to change the sign for work. Usually it is positive sign, but here we have changed the sign to negative because the work is done on the system. Okay. Now we will calculate this by using the values. The Q value is minus 20920 joules minus of minus 30,000 joules. So finally we will get a value of about 9080 joules. So this is the change in internal energy where we got 9080 joules of change in internal energy value. So in this example, we have to calculate the change in internal energy simply by using the first law of thermodynamics. Okay, we have used the first law of thermodynamics only with a little modification. For W value, we have kept negative because here the work is done on the system and heat is flowing out of the system. So we have to change the signs accordingly and we have to calculate the change in internal energy. Okay. Now the change in internal energy in this question is got about 9080 joules. So these are the examples, numerical examples that are calculated on internal energy, enthalpy and work. And we'll calculate or we'll see some more topics related to thermodynamics, that is like definitions and terminology, in the next lecture. And thank you.
Like, share and subscribe. Hit the bell icon for more updates.